Okay, good morning again, everybody. So for today, we'll start the formal discussions for Math 174. Last week, we did an orientation, and unfortunately for us, Friday was a holiday, so I wasn't able to meet you to do a review of the fundamentals of computing. Though these are topics that were supposedly covered in AMAT 152, pero nag-request kasi yung I don't know if it was you or the other section. They requested for a review, so I did a review for the section for section V, and I just recorded the discussion so you can guys can watch it during your free time last week. So that ngayon we'll go formally into the contents of Math 174. And then in the labs yesterday or on last Monday, I asked your lab instructor to give you a review about convergence of iterative algorithms. So hopefully it went well. So for this week, we'll start the coverage of Math 174, which will start with polynomial interpolation. So hold on, let me switch slides. Let's look at module 2. So hopefully you already have a copy of module 2. And as I have mentioned last time during the orientation, all the things that you need to know for a certain week is contained in our modules, and specifically don't skip the first part, which is the before you proceed part. This is the equivalent of the study guides for the week. So in here I put all the information. So I have an introduction. So here in this module, we will discuss the basic theory for polynomial interpolation. Specifically, we'll mention some important results in numerical analysis, plus take a look at the basic forms of interpolatory polynomials. So this is the suggested material for the 20th to the 24th of September. You will have the synchronous laboratory sessions for the contents of module 2 on the 27th, and the first part of laboratory exercise 1 will be due on the 27th, right before midnight. Okay. And then what to watch out for are the following. So at the end of the module, you should be able to state the Weierstrass first approximation theorem and the Unisolvance theorem. Number 2 is to discuss the significance and implications of these theorems. And then third, derive the Lagrange form of the interpolating polynomial relative to a given set of data points, along with the error estimates. So probably this week we'll be able to do objectives 1, 2, and the first half of objective 3. And then next week actually next meeting, we're going to do quantify the theoretical error incurred in interpolation. And it's kind of an integrative objective to use interpolation to solve scientific problems. So you also have here the suggested supplementary materials. Again, we tried as much as possible to put everything that you'll need in the modules. But if you want to see a more detailed discussion of some of the things here in the module, so you can consult these supplementary materials. And then at the end of this module, you will see laboratory exercise 1.1. This is the first half of exercise 1. So this is designed for 1.5 hours. So once we finish discussing things, you can start answering lab exercise 1.1. Though the due date would be right before the midnight of Monday. So that means even if you don't have time within the week to finish or to work on the exercise, you have your actual laboratory class to do the exercise. Also, take advantage of your lab instructors. They will be there to guide you if you have some questions about the exercise on Monday. Okay. But again, it's advisable to start it if you have time before Monday so that you have formulated your questions, you know what are the difficult parts of the exercise, so you can ask your laboratory instructors for specific help. Okay. Tapos medyo bantayan nyo lang kasi uploading might take a couple of minutes. So give a little allowance before the deadline when you log in into Canvas. So yeah. And again, if you cannot submit it on time due to some extraneous reason, so just let me know so I can adjust the deadline for you. Okay? So let's start. Let me shift slides again. I'm gonna use the slides I used way back in 2015. Hindi naman nagbago yung content ng interpolation or yeah, yung interpolation theory since 2015. So I'm gonna use the same set of slides. Everything in the slides is in the module and is on the work text. So you don't need to have a separate copy of this slide presentation. Gagamitin ko lang siya para divide yung mga information in several sections or several slides. Okay. Now, this chapter of Math 174 talks about approximation of functions, specifically using polynomials or polynomial-like functions. Kasi in the real world, yung mga data na makukuha natin is not in the form of functions which we learned how to manipulate in our basic calculus courses. Remember sa Math 36, 37, and 38, pag binigyan kayo ng isang function that is nicely behaved, meaning it's sufficiently smooth, marami kayong pwedeng gawin. You can do optimization, you can you can differentiate, integrate these functions, you can do a lot of things. You can analyze this using those analytic tools. However, the disconnect is in the real world, we don't get functions right away because data are usually represented in terms of discrete set of points. So kapag halimbawa, merong isang epidemic that broke in a certain region, then hindi natin makukuha yung epidemic curve, meaning we don't get a continuous function of time to model, say, the number of deaths associated to the disease, right? But instead, what we do is we collect data, and since we are finite beings, mayroong interval yung kaya nating i-collect na data. For instance, what we get as data would be the number of deaths for specific days after the outbreak. So we get 0 deaths after 0 days, 8 deaths after 10 days, and so on. And we can only do so in a finite number of time steps. Unlike in Math 36, yung mga classroom problems natin nun, ibibigay sa atin ano yung P of t. It could be exponential, it could be logarithmic, it can be a polynomial or whatnot. It would be a nicely behaved functions. Tapos, ang problema natin dito ay paano kung gusto kong maghanap ng information that is not contained in this table. For instance, I want to know how many deaths occurred, say, at day 37. Or gusto kong malaman ano yung weekly breakdown ng number of casualties due to the disease. So, hindi ko siya mahanap by just looking at this table. Pero kung meron akong function that represents the number of deaths as a function of time t, then I'll just need to plug those in the t values in and get the function value. Okay. Or if I want to get when did the maximum number of casualties occur, and what is the number and what is that number? Kung given sa akin yung function t, function p of t, then pwede kong kunin lang yung derivative, equates siya sa 0, then apply the first or the second derivative test, makukuha ko yung maximum value ni p of t over the interval 0 to 100. Pero unfortunately, by just looking at this table with only 4, or actually how many? 5 data points, I cannot know those information. But again, facing reality, this is the type of data we see in the real world. Hindi yung function talaga like the textbook problems from Math 36. Okay. Likewise, ito yung isang classic example sa Math 36 to optimize functions. So we'll be given the demand curve or the demand function for a certain commodity sa Math 36. So ibibigay yung d of x. And then kaya nating i-model yung revenue function, r of x, which is the price times the demand or the number of units sold at that particular price. And then papahanap sa atin ano yung optimal selling price. So magkano ko dapat ibenta yung product so that I'll get the maximum revenue or the gross sales for that particular product. Pero kung isa ka ng businessman, pag-graduate mo sa university, tatanungin ka ng boss mo, ano yung maximum selling price or what's the optimal selling price for our commodity? Pero ang bibigay niya sa yung data ay something like this. Say, when you sell the product at 70 pesos, you're gonna be able to sell 1,250 units. If you sell it at 82 pesos and 50 cents, you'll be able to sell 750 units and so on. Tapos tatanungin ka, magkano ko dapat siya ibenta para makuha ko yung maximum revenue? Of course, if you'll just look at this table, pwede mo siya ma-compute what's the best among the four prices by just multiplying the price and the number of units sold. Multiply mo, makukuha mo yung revenue. But you will have limited options. What if the optimal selling price lies between 70 and 187.50? Hindi mo siya makukuha by just looking at the table, so we need to do something. And that brings about a nice problem in numerical analysis. How do we get a function that will represent or that will give us an approximation of the data set? Okay, so ano yung function na pwede niyang gayahin yung trend represented by a finite and discrete set of data? Okay, and that's basically the first chunk of Math 174. So which will bring about two classic areas of study. Pero yun nga, this is used to address a common mathematical problem. So we are only given a discrete, usually finite set of points, x1, f of x1, and either we want to approximate the value of f at some value of x not included in the list. So gusto nating malaman ano yung value ng function labas dun sa data point. So katulad dun sa epidemic problem, I want to have a weekly breakdown of data. Pero hindi given yung number of casualties at t equals 7, 14, 21, until 98. Kasi apat lang binigay na data points. Or, even more general than this bullet, is sometimes you want to determine a function g that mimics the behavior of the data in some sense. Because again, if you have a function g that kind of try to imitate how the data points behave, then we can do a lot of things. We can apply those tools or some techniques we learned in our calculus courses in order to get some relevant information coming out of our data set. So these two problems give rise to two different areas of study in numerical analysis, namely interpolation and approximation. And on the next two slides, we'll try to differentiate interpolation and approximation from each other. Now, interpolation is we want the function g so that it will exactly mimic the data at the given nodes or at the given information. So ang idea ng interpolation, makakahanap tayo ng function g na dadaan eksakto dun sa data points given in the problem. So that is achieved by imposing zero errors at the given exabytes. So remember, given lang tayo kanina ng xi, f of xi, right? So dahil given sa atin na yung given sa atin itong mga data points na to, so gusto ko yung function g na mag-i-imitate doon sa dataset ay dadan eksakto doon sa mga xi, f of xi na given doon sa problem. The idea is what better way to do the approximation by fitting a function that will pass through exactly the given data points. Kaya naman, ini-impose natin tong condition na to. The f of xi, which is the given y values in the data, minus g of xi, which is the function value of the nodes or the exabytes given in the problem, under the function g, which we designed to mimic the function f, must be equal to 0. So, ibig sabihin kung given itong mga data points na to, gusto natin yung interpolating polynomial ay dadaan eksakto dun sa mga data points na yan. Okay? So, ganun natin pinipili yung function g, right? Because again, we are free to choose or we are free to design the function g. In interpolation, I am choosing g so that it's a function that passes through exactly the points given in the data. All right? So yun yung interpolation. On the other hand, when we say approximation, the function g is chosen so that some measure of error is minimized. So medyo relax yung condition sa approximation. Sa interpolation, sinabi na ano yung measure of error. So you can think of this measure of error to be a little bit a little bit local, because we are only concerned with the errors at the given exabytes. All right? So ang ini-impose lang natin, dapat 0 yung error dun sa given exabytes. We don't care about other x values na hindi given dun sa dataset. Pero theoretically, this will supposedly give us a good approximation even for points within the interval given. Kasi kung marami kang data points, tapos yung function mo dumaraan sa bawat isang exabytes, then you expect that we will get a very good approximation to the given function. Okay? Now, oh, by the way, we call this the interpolatory requirement. Again, this is requiring the approximating function to pass through all the exabytes. And the result of this approximation is an interpolating polynomial. So meanwhile, in approximation, again, we impose some measure of error. So hindi uniform ano yung measure of error na ginagamit. Kaya napaka-generic pag sinabi mong approximation of a function, because you need to give what the measure of error. So a usual measure of error that is imposed in approximation is this. I think you are familiar with this, or you have seen this before. This is the least squares error, right? You take the errors, square them up, then sum them. And we want this to be minimized or to be within some small threshold epsilon. So, ito yung ginagamit sa least squares approximation. Gusto natin maliit yung errors ng f of xi minus g of xi. Pero we don't necessarily impose the errors to be 0 at the given exabytes. So you can see here that interpolation can qualify as a specific example of approximation. Okay? Kasi mas special lang nga lang yung interpolation kasi kailangan dumaan ka eksakto dun sa mga exabytes. So ibig sa mga exabytes, f of exabytes. So parang yung interpolation connect the dots. So yung data points mo, i-plot mo in a scatter plot, tapos kailangan ma-require na yung interpolatory polynomial ay dadaan dun sa mga data points na yon. Pero in general, if you mention approximation, then there's no such a requirement. So gusto mo lang mag-minimize ng some measure of error. That's why in approximation, you can design your measure of error to be as global as possible. Hindi lang nakadepende dun sa mga exabytes yung measure mo ng error. Pero yung interpolation, medyo local yung treatment niya dun sa error na minimize niya. Because what is a better way to minimize the error by requiring 0 errors at the given exabytes? And for the next few weeks, we'll focus on interpolation. Actually, interpolation, okay, let's consider an example first. So let's consider the function f of x equals e to the x. And say we'll use the nodes -2, -1, 0, and 1. So when I mention nodes, I mean these are the exabytes, right? Or minsan tinatawag din natin silang abscissas, or the x values simply. So halimbawa gusto kong i-interpolate yung function e to the x using this point. So pwede akong gumawa ng table of data, table of data. So pwedeng ang x's ko ay -2, -1, 0, and 1. Tapos kunin ko yung f of x. So this would be e to the -2, e to the -1, then 1, and then e. So ibig sabihin, kung interpolating polynomial, yung hinahanap ko, dapat yung function g na i-form ko, dapat magpapass through sa 4 na data points na ito. So you will learn later how to compute the interpolating polynomial relative to a given set of abscissas, pero for now, believe me that what you'll get is this function p, or this polynomial p. Okay. And you can try in your own time later kung anong mangyayari kung i-plug in ko yung x equals -2, x equals -1, x equals 0, and x equals 1. So if you do so, say p of -2, you should be able to get e to the -2. If you plug in -1, you should get e to the -1. If you plug in 0, you should get 1. If you plug in 1, you should get e, because that's the interpolatory requirement that goes along with interpolation. Okay. So this is the interpolating polynomial. What we get here is what? A degree 3 polynomial, which will exactly pass through the 4 given data points. Okay. In contrast, an approximating polynomial for f could be this guy, the polynomial q. Do you guys recognize this polynomial? Anybody? Nakikilala nyo ba tong q? Or how did I obtain the function, the polynomial q? Or hindi pa rin gumagana ang brain cells? Or nasa bed pa kayo? All right, anybody who recognizes this function q? Or this polynomial q? Paano ko kaya na-derive yan? Come on, guys.
Taylor expansion po ba, sir?
Oh, yes. So thank you, Jonathan. Exactly, yeah. This is a truncation of the Taylor series expansion for e to the x. So remember, sa math 30, saan nyo ba ito ginawa? 37 or 38? Natutunan yung Taylor series expansion. So alam nyo sa e to the x, ito ay equals infinite series, x to the n over n factorial, n going from 0 to infinity. All right. So we know that e to the x is exactly this guy. All right. However, for us, or if you want to get an approximating polynomial, because this is not a polynomial, kasi ang polynomial dapat may finite number of terms, so we can cut the summation down into the first few terms in order to get an approximate for e to the x. And that's what I did here. I just retained the 4 terms. So I used n equals 3 here. Sorry, I replaced infinity, the upper bound in the summation, by 3. Okay, so you see here in the interpolating polynomial, if you plug in, say, x equals, if you plug in x equals 1, so you compute q of 1, you will get 1 plus 1 plus 1/2 plus 1/6. Obviously, this is not equal to e to the 1. All right? Kasi itong mga to ay rational numbers, pero si e ay irrational. So that means q of 1 is not exactly e to the 1. So this is not an interpolatory polynomial kasi hindi siya nag-pass through dun sa data points, or may isang data point na hindi siya dinaanan. Pero nonetheless, we learned that this is a good approximation for q of x. When I say good, relative to some degree of required accuracy. Pero let me see if I have the graphs of the two functions. So I don't have the graph here, but if we jump to module 2, I guess I have the illustration here. Okay, so in figure 2.1, we see here the graphs of y equals e to the x and the graph of the interpolating polynomial, which is of degree 3. All right. So you see here na e to the x is the blue curve, the interpolating polynomial is the red curve, and then makita niyo yung black na or blackish color ng curve kapag ka nag-intersect yung dalawang graphs. So here you see that at the 4 data points, -2, 1, -1, 0, and 1, the blue curve and the red curve intersects. Kasi ito yung interpolatory requirement. An interpolating polynomial must pass through all the given points, all right? And you see that there's a very good approximation, especially between -2 and between x equals -2 and x equals 1, which are basically the smallest and the largest abscissas in our data set, all right? So kasi almost black yung color nung curve dun sa interval -2 to 1. So we see very good approximation there. Pero sa labas nung interval na yon, medyo nag-diverge na yung dalawang curves. Naghihiwalay na sila. Pero the idea is, in an interpolating polynomial, the only requirement is mag-pass through siya dun sa apat na given na data points. And you see the effect of requiring that. Napakaganda ng approximation on this portion of the curve. All right. Now, in contrast with an approximating polynomial, which, as Jonathan suggested earlier, this is a truncation of the Taylor series expansion. You see that there is a good interval over which maganda yung approximation or magkalapit yung exponential function and the truncation of the series expansion. Pero kung makikita nyo, hindi nag-pass through sa hindi nag-intersect yung dalawang graphs sa x equals -2. And they are barely intersecting at x equals -1, as well as at x equals 1. I don't know kung nag-intersect sila sa 0. Yes, I think they intersected at 0 kasi ang function value nito at x equals 0 is also 1. Pero that's just a coincidence. Kasi in an approximation, or in approximating, in designing an approximating polynomial, hindi required na mag-pass through dun sa given data points. So basically, those two things, or this actually, the interpolatory requirement distinguishes interpolation from all other forms of approximation. Okay? Is that clear so far? Okay, I hope it is. If you have questions, just put them on the chat or just unmute yourself and interrupt me anytime. So now, why focus on interpolation? Kasi out of so many approximating functions, or out of so many ways to approximate a certain function, why we focus on interpolation? Actually, it's from it's an application from application basis. The nice thing about about interpolation in general is that it is quite simple. Okay, there is a closed form formula for building up an interpolating polynomial or an interpolating function. It is also easy to implement on a computer, and then so also this takes advantage of the given data set. Kung meron ka na nga naman data set, bakit ayaw mo pang kumuha ng isang function that will exactly give us those data points na given in the problem in the first place? Okay. Now, from a Math 174 point of view, we focused on interpolation because you will learn other approximating techniques if you go to your applied math courses, or in your math courses, or even in statistics, they do curve fitting and so on. So that's why we focus more sa 174 on interpolation, kasi I don't think there is another course that talks about interpolation. And this is a nice thing because madali siyang i-implement talaga. And it is useful in several, or in any application area. You can elect to use interpolating polynomial as your approximation. Now, there are several common forms of interpolation. We have polynomial interpolation, meaning yung function g na pipiliin natin para i-imitate yung behavior ni function f on a discrete data set ay polynomial. Pwede rin namang piecewise function yung gagamitin nating interpolating function. But some other techniques, you also have rational, trigonometric, and exponential interpolating functions. But for our class, we'll focus on polynomial and piecewise polynomial interpolation. So kung nag-iisip na kayo ngayon pa lang ng topic for your final project, you can take a look at rational, trigonometric, and exponential interpolating functions, because we will not cover these in class. So pwedeng siya yung gawin yung topic dun sa final project nyo. So you can start Googling what this or how to do rational, trigonometric, or exponential interpolation. Tingnan nyo lang ano yung advantages niya, paano siya i-apply, madali ba siyang i-program para magamit natin for large data sets. But again, in class, we'll talk more about polynomial and piecewise polynomial interpolation. Now, why focus on polynomials? Well, these are the simplest functions which are practical for computers. I say simplest kasi madaling ipagawa sa computer yung polynomial evaluation. Kasi if you evaluate a polynomial, ang kailangan nyo lang gawin ay yung four basic operations. You only need to add, subtract, multiply, and divide, possibly. Okay? So, ng mga numbers. So, ganun lang tayo nagpapa-evaluate ng polynomials. And they're very ideal for computers because they don't need the large memory to be carried out. And actually, mas mas madali siya than transcendental or other kinds of computation. So yung four basic operations lang involved. And then from a more theoretical standpoint, the derivatives and integrals of polynomials are easy to compute. And what you get back are again polynomials. Pag nag-differentiate ka, nag-integrate ka, madali lang. Meron tayong formula para sa derivatives at integrals ng polynomials. And actually, ang nakukuha natin pabalik ay polynomials pa rin. So if we are interested in getting the trend or analyzing the data on several levels, madaling computein yung derivatives, mag-evaluate ng derivatives, mag-evaluate ng integrals kasi polynomials lang uli yung makukuha natin. And polynomials are infinitely smooth. So kahit ilang differentiation yung gusto mong gawin, posible. And usually in numerics and in most applications, we want smooth functions. Kasi pag smooth yung functions, marami tayong magagawa. Most of the tools we learned in Math 36 or Math 37 can be applied. Okay. And this is one of the classical results. It says na for any required accuracy, laging may polynomial na nag-approximate kay f. So this is not limited to interpolation, but in approximation in general. So, lagi kang may makukuha polynomial. Basta si f ay continuous. Guaranteed na laging meron kang makukuhang polynomial na napakalapit ng napakalapit ng values kay function f. And you can do so even for very, very tiny errors allowed. Okay? So, formally, this is called the Weierstrass approximation theorem. So it tells us that for every continuous function f over the interval ab, you can choose any epsilon greater than 0, however small. You can always find a polynomial such that the absolute difference between your function f and the polynomial, this should be big P, is less than epsilon for all x's between ab. So remember sa math, pag sinabi natin epsilon, napakaliit na number na yan. So kahit pumili ka ng napakaliit na epsilon, lagi kang may mahanap na polynomial ng distance mula kay f sa bawat x's on the given interval ay less than epsilon. So lagi kang may mahanap na polynomial na napakalapit dun sa continuous function f. Okay, it doesn't matter how small you elect the error should be, laging may makukuha kang polynomial f. Kaya hindi tayo mauubusan ng polynomials. Kaya bawal magreklamo na, halimbawa magtanong ako, give an approximating polynomial of error 10 to the negative 20 over the interval AB. So bawal yung sabihin, sir, imposible pong makahanap ng ganung kalapit na polynomial dun sa continuous function f. Because I can just appeal to the Weierstrass approximation theorem, which says kahit anong epsilon, kahit gaano pa kaliit si epsilon, lagi dapat kayong may mahanap na polynomial f. Now, the proof of the Weierstrass approximation theorem requires some things, density of the polynomials on the space of continuous functions, and that will be beyond the coverage of the course. So probably you'll see this in advanced numerical analysis classes or probably in functional analysis. But for now, let's accept the Weierstrass approximation theorem to be a fact, right? So yung proof ay hindi nga lang suited for our level today. So, but again, this guarantees the existence of a polynomial that is very, very close to a continuous function f. So kaya pwede tayo ngayon mag-rely, pwede tayong maghanap ng approximating polynomial. Kasi sabi ng Weierstrass, lagi tayong may mahanap na polynomial na napakalapit kay function f. Okay? So, and then, if we go into polynomial interpolation or finding an interpolatory polynomial, kahit napakaraming approximating functions for a certain function f, okay? Meron lamang isa. There is one and only one interpolating polynomial for a given set of data points. So ibig sabihin, unique yung interpolating polynomial for a set of data points. And formally, I will define here what an algebraic interpolating polynomial is. So a polynomial p sub n of x of degree no greater than n, okay? So basically, yung polynomial p sub n, ito yung interpolating polynomial. It is of degree no greater than n, so n yung maximum degree niya. And this is relative to what? Of course, you have the indeterminate x or the variable x. Itong pagko-compute ng Pn nakadepende rin sa function f that you want to interpolate and on the given x subice. So kailangan mo itong mga parameters na to para mag-build ng algebraic interpolating polynomial. So kailangan mo yung function f to be interpolated and the given x subice. And then of course, it's a polynomial of degree no greater than n. So ganito yung magiging itsura niya for some constant c, correct? C sub i's. And this will coincide with the data points x sub I, f of xi for all the given x sub i's. So ito lang yung interpolatory requirement. And this polynomial p sub n is called the algebraic interpolating polynomial. So ito na yung kanina pa nating minimension, pero I just put it here formally. So ano yung ibig sabihin ng interpolating polynomial? Okay. And then as promised, we have the Unisolvance Theorem. Ano yung Unisolvance Theorem? It tells us that there is a unique algebraic interpolating polynomial. So again, kahit anong function pa yung ibigay nyo sa akin, or kahit anong pang data sets consisting of n plus 1 data points, lagi akong may mahanap na algebraic interpolating polynomial of degree no greater than n. And that algebraic interpolating polynomial is unique. So kahit magdoodle ako dyan ng kahit anong data points, okay? Lagi ako may mahanap na interpolating polynomial na dadaan sa lahat ng points na yan. And actually, not just that. Unique yung makukuha kong algebraic interpolating polynomial, right? And of course, since we do have a very huge claim here, medyo heavy yung claim ng Unisolvance Theorem, then let's try to prove the Unisolvance Theorem. Okay. So, and then in your module, I do have the actual proof there. I don't know if you already read this, pero hold on. Okay, the Unisolvance theorem here is theorem 2.2. So it says here again, for any set of points with distinct abscissas x sub I, f of x sub I, there exists a unique algebraic interpolating polynomial. So the claim here is twofold. We are claiming the existence of an algebraic interpolating polynomial, and we have a second claim. We're saying that interpolating polynomial is unique. So twofold yung magiging proof. Proof of existence and then proof of uniqueness. Now, to prove existence, one way to do so is to give me a formula for the algebraic interpolating polynomial. So in this page, we do have here the form for the interpolating polynomial. So it says here na, okay, consider p sub n of x to be the summation of f of x sub k, L sub k of x, k going from 1 to n plus 1. So we don't have any problem with the f of x case. These are the given function values for x sub k, k going from 1 until n plus 1. So sila lang yung mga given function values mula sa data. So they are constants. And then the L sub k's here are actually these guys. They're actually the polynomials. Nandyan yung variable x. And actually we call this the Lagrange basis polynomials. Okay. And how do we get the Lagrange basis polynomial? So for a fixed k, and k takes values from 1 to n plus 1, yung Lagrange basis polynomial ay product ng mga rational expressions of the form x minus xi over xk minus xi, where I is a number from 1 to n plus 1, but I is not equal to k. And actually, it's easy to see why we don't allow I to be equal to k. Because if we do so, magkakaroon ka ng zero denominator. So ayaw natin yung k maging equal kay I. Okay? So kung i-expand nyo yung L sub k, wala pala dito, pero kung i-expand nyo si L sub k, gagawa nyo lang siya ng x minus x1, tapos x minus x2. Okay, maybe we can do that here. So this is x minus x1, x minus x2, hanggang x minus x sub j, x sub k minus 1. Tapos liligtangan niyo yung x sub k kasi hindi pwedeng I equal kay k. So ang susunod sa x minus xk ay x minus xk plus 1 times dire-diretso na to hanggang x minus x sub n plus 1. And then yung mga denominator ay xk minus x1, xk minus x2, xk minus xk minus 1, xk minus x sub k plus 1, hanggang x sub k minus x sub n plus 1. Kaya madaling tandaan kung ano yung itsura ng mga Lagrange basis polynomials. Kasi pwede nyo gawin x minus x sub lahat ng x sub i's, maliban lamang dun sa kaparehas na k. Alright? Kasi magsi-zero yung denominator. So that's how you form the Lagrange interpolating polynomial. Okay? And actually, ilan yung factors na nasa bawat isang L sub k? Can you tell me ilang factors meron dyan? Do you agree meron ka lang n factors? Kasi gagawin natin yung product for all i's from 1 to n plus 1. So there would be a total of n plus 1 factors. Pero si I hindi dapat equal kay k. So mababawasan ng isa yung mga factors. So we will be down to n factors of this form. So, ibig sabihin si L sub k ay degree n. Okay? And then si f of xk ay constant. So basically Pn is the sum of constant times a polynomial of degree n. So ibig sabihin kung walang cancellation na mangyayari, si P ay degree n. Kung may cancellation na magaganap, then P sub n could be of degree less than n. Pero never lalampas sa degree n si P. Kasi bawat LK ay degree n lamang. Right? So hindi na dadagdagan yung degree by simply adding polynomials up. Okay? So that means indeed P sub n is of degree no greater than n. So yung isang criteria sa pagiging algebraic interpolating polynomial is satisfied na. Okay. Now let's see if the interpolatory requirement is satisfied. And we can do so by evaluating yung L sub k. So if I will plug in into an L sub k, isa dun sa mga Lagrange interpolating polynomial, yung isang x sub I na given dun sa problem, okay? So remember, ang itsura lang ng Lagrange polynomial ay ito. Wala ka lang factor of the form x minus x k over xk minus xk kasi mag-zero yung denominator. Alright? So what I did here is kinuha ko lahat ng posibleng factor pero hindi kasama si x minus xk kasi yung denominator niya magiging xk minus xk. Tapos pinlogin ko lang si x sub j. Right? And then let's try to compute what this function value is. Kapag si k ay equal kay j, okay, so ibig sabihin lamang lahat ng k ay mapapalitan ng j. Okay, lahat ng k mapapalitan ng j. So ibig sabihin, makakancel to, makakancel yan, makakancel yan, cancel yan, cancel yan. So puro product ng mga ones. So that's why when k is equal to j, this guy evaluates to 1. Alright? Pero kapag si k ay equal kay j, ibig sabihin, isa sa mga factors na to ay posibleng ganito yung itsura. So, posibleng meron ako ditong x j minus xj. Sorry. Ano yung magiging itsura niya? Di ba LK to? So, ibig sabihin meron akong x minus xj over xk minus xj. Since k is not equal to j, may isang factor ng itsura niya ay x minus xj over xk minus xj. And if I plug in xj for x's, so itong una, yung minuend sa numerator ay magiging xj. So ibig sabihin, may isang factor dito na xj minus xj all over xk minus xj. So that means 0 yung magiging product. So basically, the Lagrange polynomials, when I plug in the xj's, may dalawa lang posibleng values. It could be equal to 1, it could be equal to 0. And it will be equal to 1 even only if k is equal to j. All right? Now, what's the good thing about that? Well, if we compute p sub n, evaluated at xj, ibig sabihin, yung mga Lagrange polynomials, nagzi-zero lang sila kapag si j ay not equal kay k. So, ibig sabihin, isa lamang yung non-zero terms dun sa summation. Okay. So, nangyayari ay dun sa jth term, so remember this is f of xj times L sub j, x sub j. So, ito ay equal dyan, dun sa summation, right? But we knew earlier that when I have k equal to j, yung Lagrange polynomial ay equal lang kay 1. Pero otherwise, kapag si k ay not equal to j, like this one, if j is not equal to 1, then the first Lagrange polynomial is equal to 0, evaluated at x1. Also here, magzi-zero siya, magzi-zero siya, magzi-zero siya, magzi-zero siya. And when we sum them up, we get f of x sub j. So dapat subscripto x sub j. And so what we learned here is that p sub n of xj is equal to f of xj. So that means the interpolatory requirement is satisfied. Okay? All right, is that clear? So ibig sabihin talagang si Pn, as defined here in this equation, is an interpolating polynomial. So unfortunately, it's already 9:20. So if it's, will it be okay if I borrow 5 more minutes and hopefully we'll finish the proof before I dismiss you? Okay. Okay, thank you. Any questions about the proof? Quick questions? Clear naman yung proof. I think I just have a little typo here, pero yeah, dapat meron ako ditong xj minus xj over xk minus x sub k minus 1. So let me fix this. Pero I hope you get the idea. Okay? So ano pa yung kulang natin sa proof? Na-prove na natin na, yeah, may nag-exist. And one way to compute it is using this formula, the Lagrange form. Okay? Now, ang utang pa natin dun sa proof is to show na unique yung interpolating polynomial, meaning we cannot find any other distinct interpolating polynomial for the given data points. Now, this is a usual trick. Hopefully, you have seen this in your proving classes, Math 101 or kahit sa Math 36. Nakita nyo na siguro to. When we are trying to prove uniqueness, we try to assume na meron dalawang magkaibang interpolating polynomial. And here I call them P and Q. So kunwari may dalawa. So kung may dalawa, tawagin ko siyang P and Q, i-define ko yung function R to be P minus Q. Alright? So what can we say about the function R? So si function R ay difference lamang ng polynomial P of degree no greater than n. Si Q ay polynomial then of degree not greater than n. Okay? So ano yung degree ni R? So, kung itong dalawa ang degree nila ay hindi lalampas ng n, so dapat ang degree ni R dapat ay hindi rin lalampas ng n. Right? Pag nag-add ka ng polynomials, hindi naman nadadagdagan yung degree. Posibleng mabawasan pero hindi nadadagdagan yung degree. So R is still of degree less than or equal to n. Okay? And then, since P and Q are both interpolatory polynomials, ibig sabihin pag pinlog in ko sa kanila, yung mga given x sub j's, okay? Parehas sila ng function value kasi interpolatory polynomials silang parehas. So, ibig sabihin, P of x j I, f of x j. Ang Q of x j I, f of x j. So, meaning R of x j turns out to be 0 for all the x sub j's. Pero ilan yung x sub j's natin? Meron tayong n plus 1 na x sub j's. And I say there is a contradiction here. Ano kaya yung contradiction? Anyone? Still have 2 minutes. Nasaan kaya, bakit kaya may contradiction? Actually, technically hindi contradiction, pero I'll be forced to say that R is the zero polynomial. Bakit? Anyone?
Sir,
Yes?
ano po kasi sir, sabi po kasi suppose that there exist two algebraic interpolating polynomials P and Q. So, inassume po natin at first na magkaiba po si P and Q na interpolating polynomials ng R. Kaso po nung nagpasok po tayo ng x sub j po sa P of x sub j minus Q x sub j, same lang po sila ng function value. So, dahil po 0 po yung difference nila. So, therefore po, contradicting po siya na magkaiba pero yung function value po pala nila ay same.
Yeah, pero the problem there is parehas lang sila ng function value sa mga x sub j's. Pero hindi sinabi na parehas sila sa lahat ng x's. So, posibleng meron kang data point na ganito. Ba, ito yung mga data points natin. Okay. So, pwedeng si P, ganito yung itsura. Tapos, posibleng si Q, ganito naman yung itsura. Okay? So, parehas silang interpolatory polynomials kasi dumaan sila dun sa lahat ng data points. Pero P is different from Q kasi for x's beyond the interpolatory polynomials, magkaiba yung function values nila. So, kaya technically dito, wala pa ako na-violate. Alright? Pero, yeah. The reason why we can conclude actually that P is equal to Q for all x's, not just the x sub j's, is through the fundamental theorem of algebra. Ano yung sabi ng fundamental theorem of algebra? Natatandaan niyo pa ba? Yung FTA. Sabi ng FTA, if you have a polynomial of degree n greater than 0, will always have at most n roots. Okay? So kapag meron kang polynomial of degree n greater than 0, sabi ng fundamental theorem of algebra, lagi ka lang magkakaroon ng at most n roots. Ibig sabihin, p of x will be equal to 0 for at most n values of x. Alright? Kaya kung meron kang quadratic polynomial, meron ka lang at most dalawang roots. Kung meron kang cubic polynomial, at most tatlo lang yung roots, so yung intersection niya with the x-axis. But what do we have here? We have a function r na ang degree niya ay less than or equal to n. So ibig sabihin, at the most, ang degree ni r ay n. So ibig sabihin, mag-expect tayo ng at most n roots lamang para kay r. Tama ba? So ang degree niya ay pinakamataas na yung n. So ibig sabihin, hindi siya pwedeng magkaroon ng roots na lampas ng n. Pero what have we found out here? We found out na si r ay nagze-zero sa lahat ng xj. Pero ilan yung mga xj's? Meron tayong n plus 1 na x sub j's. So ibig sabihin, na-violate natin yung mabaviolate yung conclusion ng fundamental theorem of algebra. So that means R should have degree equal to 0. At isa lang naman yung polynomial of degree 0 na ang function value ay 0. Ibig sabihin, R should be the 0 polynomial. So R of x must be the 0 polynomial. Though nice tries, Christine. I think I know what you're getting at. But this is the precise reason why mafo-force tayo ng R of x ay equal kay 0 for all x's. Hindi lamang dun sa mga x sub j's. Kasi kung papayag tayo na ang degree niya ay greater than 0, tapos meron siyang n plus 1 roots, which are exactly the given x sub j's, mabaviolate natin yung fundamental theorem of algebra. So to avoid that absurdity, we were forced to conclude that R of x is identically 0 for all x's. But what is R? R is px minus qx. And we're saying it is equal to 0. That means p of x is equal to q of x for all x's. Okay? Now, I hope that's clear. Clear ba yung proof? At least yung existence and at least yung uniqueness. We'll go through the uniqueness again kasi if you pinasadahan lang natin yung formula kung paano nagkaroon ng interpolating polynomial, okay, of this form. Babalikan natin yan next meeting when we go to the Lagrange form of the interpolating polynomial. Right? But I hope the theory behind the conclusion that it is unique is clear. Okay. Now, next meeting we'll talk about this formula for the interpolating polynomial, and we will use this formula in order to solve some elementary problems related to polynomial interpolation. Una, gagawin natin siya sa maliliit na data set para pwede natin siyang gawing mano-mano to guide our intuition into understanding the formula. And then we'll try to answer some more interested problem, probably using a computer program. Okay? At babalikan natin yung epidemic at saka yung salesman problem natin kanina. All right? So any questions? We only have 1 minute left. Some quick thoughts or questions? Wala naman. So let's call it a day there. Thank you guys for coming. I know it's early. It's hard for me. It's probably also hard for you. But yeah, thank you for coming. I hope you enjoyed the rest of the day. And let's see each other again on Friday. Okay, bye everyone.